Okay, so we just resume from randomized SVD part and then spectral clustering, and we'll finish. So today, I'm hoping we can close it a bit early because there isn't much. Okay, so we were this is where we stopped, right? So this low rank approximation is where we stopped. The sum of first k rank 1 matrices is what we are looking at, and so the matrix that is important is this UK transpose, right? So the first k left singular vectors, and UK transpose A is nothing but the low rank approximation, best rank k approximation. So, and this is the best possible error that you can get. Any other rank k matrix is going to have an error more than this, right? So this is the best possible error. So this is where we stop. Now, so that is naive SVD. So the naive SVD is going to have O of mn square complexity. So if you have m greater than n, you have O of mn square complexity. So the goal is now to see if we can make it faster, right? So the basic idea, as Prof mentions, is to focus on this U transpose matrix, right? UK transpose matrix. Now, the main idea is that it's not necessary to have exactly UK. So it could be some orthonormal list of vectors whose span is the same as span of UK. So when I say span of UK, it is the span of the columns of the matrix, right? So as long as Q is an list matrix having orthonormal columns with span equal to span UK, then QQ transpose will be the same as UK transpose, right? So both are actually one and the same projection matrix. So this is the idea, this is the first idea that we are going to use. So if you can find a Q that satisfies this, then we'll proceed based on that idea. So all this is in the lecture. So I'm just quickly mentioning what you need to know. So you start with Q transpose A, you split it into two parts, right? So you first look at Q transpose A, which is a much smaller matrix. It's K cross N. Therefore, you can go ahead and perform the SVD on it. So that will take only nk square, right? O of nk square, because k is the smaller dimension here, right? So in mn square will now become O of nk square, SVD of B. So all these are exact. There's no approximation so far. So all these are exact. So I have listed down the dimensions here. So once you have the SVD of B, you just pre-multiply by Q, and then you retain sigma and V here, and you call them sigma hat, V hat. So finally, this whole thing is O of M and K, because somewhere you'll have, so this multiplication, for example, is K cross M into M cross N, right? So it's O of M and K. And here also you have M cross K, and you have, so this is fine, but this is O M and K. So that will dominate. So finally you have O of M and K. So Mn square to O of M and K, right? So that is AK. So all this is exact. So there are no approximations so far. Now the problem, as you know, is Q is not available to us, right? So Q has to be. So if you had Q, then we are already done. So that's where the whole problem is. And so what do you do in that case? You use randomness. That's where randomness comes in randomized SVD, right? How do you get hold of Q? So the way you do it is from what is called the sketch of a matrix. So this is the main concept here, right? So there are a couple of things we need to remember here. Once again, this UK is this important matrix, right? So there are two things about UK. First is that it is a subspace of span A, right? So span A is what? It's the span of the columns of A. So column space of A. So span A is the column space of A, and UK, the columns of UK actually span a smaller subspace which is sitting inside the column space of A, right? So this is first idea. The first idea is that this is in fact sitting inside span of A, right? So that's the first idea. The second is it is not some random subspace sitting inside span of A. It is in fact one of the most important subspaces, right? It has the most information about it. So that is the second point. So it's a important subspace sitting inside span A. So that is the first point. Second point is, of course, that the UIs, right? The left singular vectors are nothing but eigenvectors of AA transpose. They are one and the same. Right. So how is this useful? This is useful. This will help us in the randomization part. So you pick a omega at random from the multivariate standard normal distribution. So this is, you're picking this up in Rn, right? So this is omega is in Rn, okay? And you use the components of omega to randomly combine the columns of A. So A omega is a random linear combination of columns of A, and that is also a random vector, but it's a random vector that is in Rm, right? So A omega is a span of the columns of A, right? So this will also lie in the column space of A. So that's where we are making use of the first part, right? So you are essentially still in the span of somewhere in the span of A, right? So that's a positive. The second thing is the covariance matrix is AA transpose, right? So now how do we make use of that? So if we keep sampling from this distribution, right? So A omega, so you can think of A omega multiplying A by omega as nothing but drawing a point at random from this multivariate distribution with zero mean and A transpose covariance. So what does this look like? So it's a very small example to visualize this. So assume that you have UK. So in this case, K is equal to 2, right? So you are looking at rank 2. So you want to find out the top two left singular vectors, the span of that space. You want to approximate that. So you want some Q to approximate span of U2, right? So that is your goal. Now you don't know Q, but the hope is by sampling randomly from this distribution, you can kind of approximate this subspace, right? So what will happen if you sample randomly from this? Most of the points are going to end up in this manner, right? So if you think about this as a point cloud, so the point cloud will roughly be occupying this elliptical region, okay? And U1 is the first eigenvector, the eigenvector along which the maximum information lies, right? So that is, if you remember the PCA that we did, right? So eigenvector principal component 1, which is U1, that is where most of the information is going to lie. If you flip it in terms of drawing samples from the distribution, most of the samples are going to be distributed along this line, right? So, and some of the energy is going to go around this line. And if you can think of this whole thing lying in R3, there would be something pointing out of the screen perpendicular. There'll be very small amount of energy in that direction. So by sampling, by linearly combining the columns of A randomly using a Gaussian vector, what you have achieved is that you have ended up with a set of vectors whose span approximates span of U1, U2. Okay, so that's the basic idea. So now what you do in addition is you have K equal to 2. So, but then you also oversample, meaning it's some kind of a safety net, right? So you can't promise that if you sample 2, you will exactly get span of U1, U2, right? It's the whole thing is an approximation. So this is like a safety net to say that let me sample a few more vectors so that I increase my chances of covering span of U1, U2. Okay, so that's this oversampling parameter. So literature says that this needn't be too big. So P approximately equal to 5 or 10 does the job apparently. Okay, so that's what research papers are telling us. So P equal to 5 or 10. So typically K will not be as small as 2, right? So you are looking at a huge matrix. So K may be something like 100 or 50, right? So compared to that, P equal to 5 or 10 is not too big. Okay, so that's the idea of this randomization, using randomization to get at Q. So once you have that, the rest of it is going back to the lecture. So you have L equal to K plus P, and each column is one such random vector. So there are L such columns, and A times omega will give you this is what is finally called the sketch, right? So So there are L random linear combinations of the columns of A, and the hope is that this, once you orthonormalize this, you have Q in place, and that Q is somewhat a good approximation for UK, right? So that's the idea. So now you go back to the algorithm. So the algorithm is once this is done, the algorithm is quite straightforward. So there are 5 steps, right? So first thing is you get hold of the random matrix, and this is of shape n cross L. Okay, so I'm using D instead of D, I'm using N. So M cross N. In the lectures, it's M cross D. So that's the only change. So this is shape is n cross L, and complexity, assuming each element can be generated in constant time, it's in NL, right? So that is step 0. Step 1 is get the sketch, and this is the most time consuming step, right? So O of MNL. And once you do that, the rest of it follows, right? So you orthonormalize the columns of Y to get Q. You use the QR Gram-Schmidt process or whatever. So QR decomposition will give you Q and R. You want only Q, right? So the orthonormal basis for the column space of Y. That's what you want. So you retain that, and then you multiply Q transpose with A, and then do the SVD of that. So you end up with U tilde, sigma tilde, V tilde, and then you retain the K top K vectors, or the first K vectors in U tilde and sigma tilde. You call them UK hat, so UK tilde, sigma K tilde, and then you pre-multiply by Q. Okay, so rest of it is the same. So this is the whole algorithm. So all of this you need to know. You also need to know the complexities individually for each step. So okay, so this is randomized SVD. Same thing in the lectures, nothing new. So before I go to this power iteration thing, there are these inequalities which I am hoping you would take from the slides, right? I'm not covering them. So how good an approximation is this? With a very high probability, we can say that QQ transpose A is close to A, right? All that there is one big formula. So there is sigma K plus 1 into 1 plus epsilon. So you don't need to really memorize all that. Okay, so that's too complicated. So root of K plus P, something's there, right? So you don't need to memorize that. Just the main thing you have to note there is the error is going to be strictly more than sigma K plus 1, right? Sigma K plus 1 is the best error possible. Obviously, you can't achieve that. Therefore, it is sigma K plus 1 into 1 plus some epsilon, and that epsilon in turn depends on K, these parameters K, P, and all that. Okay, so as long as you know that outline, it's enough. You don't need to memorize the exact bound or the 1 minus delta probability. All that you don't need to memorize. Okay, so that is that. So this next one, right? So this power iteration, it's slightly tricky. So it's actually called subspace iteration in the literature. So the basic idea is the following, right? Instead of doing it with A, if you perform the same sketch and all that with A transpose power Q times A, then the decay in the singular values is going to be much more prominent, right? Because you're raising them to the power 2k plus 2q plus 1, right? So this is going to give you much better results. I'll only discuss the main place where the iteration part comes, right? So instead of A, so assume that Q is 0, right? If Q is 0, you get back randomized SVD without the iteration, subspace iteration part, okay, or power iteration. But once you bring in this, you perform C omega. Instead of A omega, it is C omega. And then you orthonormalize the columns of Y to get Q, right? So where does this power iteration part come in? It comes in here, right? Only for estimating Q. So the whole power iteration procedure sits inside, so where does it sit inside? So it sits inside this step. So steps 1 and 2, you would have in the original case it was A omega. Now it is going to be C omega. So steps 1 to 2, in between that you have this procedure coming in, subspace iteration or power iteration. So what is happening is you start with A omega, right, as before, and then you orthonormalize. Okay, if you just return Q, it's the same algorithm as I said before, right? This corresponds to the case of Q equal to 0. But you don't do that. If you want A transpose power Q, you need to multiply by A transpose and then pre-multiply by A. You need to do this Q times. Okay. So that's what you do. You do it in 2 steps because otherwise the complexity will just blow up, right? If you multiply A transpose and then pre-multiply by that, that's a problem. So you do it in 2 steps. But then what you do is you interleave each A transpose multiplication with this orthonormalization step. Okay, so apparently this is needed because for some, from what I read, it's some numerical efficiency or numerical stability is what they're saying. But actually, I didn't quite get exactly why this normalization is interleaved. Because if you think about it, you can do this normalization just once, right? So what you need, the ortho of y comes in only at the end. But that's not the case. What you do is you do it after every iteration. Okay, so in the slides, this is given slightly differently. If you go back to the slides, I don't know if you have spotted it, but this q is inside, sitting inside, and when you exit out of the loop, that q doesn't come out at all. So it's like it has not been multiplied q times. So that there's some issue, if I'm not mistaken, with the slides in this particular section. So you first orthonormalize before even going into the for loop, and then you do it q times. So that gives you A transpose power q into A. Okay, so that is mainly what you need to know with respect to randomized SVD. Okay, so that's all I had for randomized SVD. So can we move to spectral clustering part? Is that fine?
Yes.
Okay, so spectral clustering, there is yeah. So before I move on, right, there is one more thing that I wanted to ask all of you. So do you all know what a cosine similarity metric is? Have you all come across this in other courses?
Maths 2 and MLF also.
Okay, so do you all know the formula for the same? So what is cosine similarity between two vectors? Okay, so if you know it, good enough. If not, please uh, note it down. So we didn't cover it explicitly in this course, the cosine similarity between two vectors. So that might be of help to you in tomorrow's exam, right? So I have just a heads up. So otherwise, later on, you must not come and tell me that you are not at all informed about this. So I'm just telling you now. So cosine similarity is a distance metric that you might want to revise a bit before showing up for tomorrow. Okay, not tomorrow, I mean Sunday. Okay, so that is there. So yeah, so that was regarding cosine similarity. K means and yeah, audio problems is there. Are you able to hear me properly?
Yes,
I can hear. Yeah.
Okay, right. Yeah, spectral clustering. So these clusters produced in K means, that is what we begin with, right? So these are Voronoi regions, and you can't really expect all possible data sets to strictly conform to this assumption that they will neatly separate into Voronoi regions. So what are these Voronoi regions? One property is that they are convex. Okay, so not all regions are convex. So what is a convex set? It's good to know this. So you have a set is S is said to be convex if you take any 2 points in the set, and if you take a line joining them, all points on the line should also lie in that set, right? So mathematically, you have lambda x plus 1 minus lambda y belongs to S for every lambda in 0 to 1, right? So if lambda exceeds 0, 1, it becomes the remaining line, and it doesn't really hold for the remaining line, right? So anything connecting the 2 points, all the points on that line segment should lie inside the set. Okay, so that is convexity. So we now move to this idea of inducing a graph given a set of data points, right? So that's where we start in spectral clustering. So you have x1 to xn, you induce a graph, meaning you have edges between every pair of points. So if you have xi, xj, then you add an edge between xi and xj, and you give it a weight. So the weight is this function, right? E power. So this similar to the Gaussian kernel that we studied, and so that's the closer they are, higher the value, right? So, and farther apart they are, smaller the value. So that is the weight. Now you can construct an undirected weighted graph. Okay, vertices V, edges E, W. So in the exam also, what we'll do is we'll call all vertices using numbers, right? So integers 1 to n, and every edge is there for a general data set D like this, but that's not always the case. I'll come to that. So Wij is the weight connecting edges I and j. So what are cuts? So cut is nothing but, so this cut terminology, right? So sometimes we think of it as a partition of the set of vertices, but we also abuse the notation and we use cut to refer to the value of the sum of the weights going across the cut. Okay, so this cut is used in two senses. I hope you're okay with that. So it could mean the partition A, B slash A, and it simultaneously, depending on the context, it also means the value of the cut. Okay, so depending on the context, you should be able to distinguish that, right? So this is the sum of the edge weights going across the cut. So in this case, for a small example, is also there in the note. So if you have this kind of a graph, now the cut is nothing but the sum of these four edges. So in this case, A is 1, 2, 3, B slash A is 4, 5, 6, 7, and the cut will be W 24, 27, 25, 26, right? The sum of those weights. Now, in general, the graphs that we give you, right? There are two types of problems that you could get in spectral clustering. One is you are given a data set like this, right? So a data set of, let's say, n points, 5 points in R2, right? And then you are asked to induce a graph using this distance metric. Okay, this one you have to memorize, right? So this distance metric. In that case, the graph that you end up with will be a fully connected graph, right? So it will be a very dense, fully connected graph with edges and edge weights going between every pair of data points. Okay. Now that is one type of problem, and then you have the Laplacian and eigenvalues, eigenvectors, all that, right? So that is one class of problems. The other class of problems is something like this, where you will be given the graph to begin with. You don't have to induce the graph. You will already be given the graph. So here there is no notion of data points, so to speak. So you have already converted them to nodes of some graph. Okay. So this may not be fully connected. So for example, 1 to 4 is not there, 3 to 6 is not there. So the corresponding weights will be 0. Okay. So, and then you can ask the same set of questions based on this graph, right? So these are largely two classes of problems that you can expect in spectral clustering. Okay. So that is the cut. And yeah, so the farther apart the points are, the smaller the weight. So you are essentially want to minimize the cut. So some more notation. So if a point, if a node is inside the set A, then we give fi 1, otherwise it's 0. So the cut therefore becomes fi into 1 minus fj wij. So this is a double summation. So you already know how this is derived. So I'm not going into the derivation and all that. So yeah, and this f is a vector. It's a binary vector, right? So 0 and 1. Each element is 0 or 1. And as an example, if you have a graph like this, right? So if you look at A as 3, 4. Okay. So F3 and F4 are 1. F1 and F2 are 0. And if you look at the cut for A, so the value of the cut is going to be, so you can either evaluate this, but you can also just eyeball, right? So 3 and 4 are in one set, right? So this weight is not going to matter. Anything going between 3, 4 and 1, 2 will matter. So the 2, 3, 2, 4, and what else? 1, 4, right? So these three weights, the sum of them will be the value of the cut. Okay. So that is one example for cut, and then you want to minimize the cuts. So this is the same optimization problem that you can see in the lectures. So I've just copied things here, right? So nothing new. So you have to define the Laplacian as d minus w. So what is w? W is the set of it's the weight matrix. So d is nothing but, you can think of d as the sum of the edge weights going out of a node I, right? So for example, if you have node 3, right, the D33 will be W23 plus W34 in this case, right? So it's the sum of it's in some sense the out degree if all the weights were 1, right? So if, for example, if this was 1, 1, 1, 1, then D33 will be nothing but the out degree of, or degree, it's all undirected, right? So it's the degree of node 3. That's one way of thinking about it, but it's not exactly the degree because you're summing across the weights, right? So it's the out weight, if you can put it that way, for the ith node. So that is dii. So the d is diagonal. D minus w will give you the Laplacian, and all of these are n cross n square matrices, right? So now this whole cut therefore becomes, the value of the cut becomes f transpose LF. So you could either say that the cut is this expression, or you could say that it is f transpose LF. Okay, so this is a quadratic form, so you remember from MLF. So that's what you have there. So this problem is hard to solve, and you have a couple of degenerate cases. So one corresponds to, both of them are in fact symmetrical, right? So this corresponds to all the points belonging to the set A, all the vertices in set A. This corresponds to all of them belonging to A complement, right? So both of them are degenerate, and the cut's value is essentially 0, right? So there is nothing useful that you can say. All of them belong to one cluster, so you kind of have to rule them out. This, coupled with the fact that it's computationally hard to solve this problem, you relax it. So the relaxation is by moving to real numbers. So you have the same f transpose LF, but then you are looking at only unit norm vectors f. So f is no longer a binary vector, it's a real vector, and f is orthogonal to 1. So f cannot be 0, as you can see, it's unit norm, so can't be 0, and it can't be 1 also because of the additional constraint. Okay, so yeah, this is the relaxation, and then you try to understand. So just try to understand this Laplacian a bit more. There are two ways of expressing the Laplacian and the quadratic form. One is, this is one way, right? So this is, any quadratic form can be expanded as Lij, Fij, double summation. Okay, so that's one way of expanding any quadratic form. In this case, additionally, there is one more form. So this is one of the questions in the graded assignment, right? One of the options. So and this is useful because this allows you to see some nice properties of the Laplacian. So one of which is that it's a positive semi-definite, meaning it is always non-negative, right? So if you look at f transpose LF, it can never be negative. So that comes from the fact that all the weights are positive and you are multiplying it by the squared difference of fi and fj, right? So this is always non-negative. So it's positive semi-definite. So that means that the eigenvalues are always non-negative. And those of you who had seen the discussion in the group, you would know that if the graph is having only one connected component, then there is only one zero eigenvalue. If not, you could have multiple eigenvalues, and one is always an eigenvector corresponding to the eigenvalue 0. So all this is standard results you need to know. So yeah, then we come to spectral clustering. So you just take the eigen decomposition of L. Lambda 1, F1 are anyway useless because lambda 1 is 0, F1 is vector of ones. So you start from lambda 2 to lambda n. So this is the solution of the optimization problem. So this should be reminiscent of PCA that we studied, right? There it was a maximization, here it's a minimization. So there it was the maximum eigenvalue, here it's the minimum eigenvalue, but because of these constraints, it's the smallest positive eigenvalue, right? So lambda 2, and the argmin will be the vector that minimizes this will be f2, right? So now you kind of extend this idea and come up with k such sorry yeah n remaining yeah, so these are, you should look at the k columns here, right? So yeah, each column is an eigenvector. So and what you do is, instead of looking at it as columns, you start looking at it as rows, and you start treating each row as some kind of a view or an embedding, right? So this gives you a representation of the data point in some other space, which hopefully captures some structure, right? So this is like V1 to Vn, all of them are in Rk, so they are all normalized to 1. So they're all in Rk, and you get this new data set of embeddings, and then you can run k-means on D prime. So in the exam, right, we won't ask you to do the whole thing, so that will take just way too much time, but you must know conceptually what happens in spectral clustering. So all this happens. So for example, we might ask you what is the view or the embedding corresponding to this particular data point. So that's a possible question, right? So these are all things you have to keep in mind. Okay, so that is mainly spectral clustering at scale. What we want you to remember is that this is a hard problem to solve. So the graph is dense. The Laplacian getting the eigenvalues, eigenvectors is hard. Therefore, we have to find ways of sparsifying the graph. And there are many sparsification techniques. We study only one technique, which is called the spectral sparsification, which is epsilon spectral sparsification, where we try to preserve the Laplacian, the quadratic form corresponding to the Laplacian. Okay, so that's the main idea. So you throw away some edges. So V always remains the same. It is only the edges that you're going to throw away. You're not going to throw away them deterministically. You are going to throw away them probabilistically, or you're going to retain them probabilistically. So with probability P UV, you will retain. Okay, this is an error. This has to be E, right? So this, no, this is F. This is E, correct? Yeah. So with probability P UV, you retain an edge in E, right? So E is, remember, UV is in E already. You are retaining it in F with this probability, and you are inversely scaling that new weight here. So why you are doing this will become apparent very soon, right? So this is the spectral sparsification. So in the last quiz, we had a question around this. So last quiz or assignment, I don't know. So we just asked which of this is the valid statement for an epsilon spectral sparsification. I think it was as simple as that. So this is the, so remember where LH should come, right? So this is what you have here. And on the LHS and RHS, you have LG, right? The quadratic form corresponding to LG. Okay, so that is epsilon spectral sparsification. And in expectation, so the nice part about this is that, so LH is random, by the way. So the whole thing is random. So the H is random because of randomness in the way you are retaining edges, right? So if H itself, the graph itself is random, then naturally its Laplacian is random. So this LH is the random quantity here. That's the random matrix. So the expectation is over all possible graphs that you can generate by this process, right? So that is, the randomness is over that. So on an average, you tend to preserve the Laplacian, right? So on an average, you get the same, not the Laplacian, the quadratic form, right? On an average, that's what you do. But then if you go back to JL lemma, right? So norm expected value of norm mu square is u square. So, but that is not the most important thing, right? You also need to know how it concentrates around the mean. Okay, so that for the concentration part, it is important to know how to choose the probability, right? So it won't concentrate appropriately for any kind of PUV. So you have to choose PUV in a suitable manner. So that is where you have this whole effective resistance, all that coming in. Okay, so key ideas we already discussed. So yeah, the choice of PUV is again something that's hard to test from our side because it involves the pseudo inverse and all that. And numerically, we haven't taught you how to compute that pseudo inverse. So but we can ask maybe questions around this, right? So what is the form taken by PUV? So questions like this could come out of it. And what is the guarantee on the number of edges? Okay, the number of edges is much less than V square, right? So N square is a very dense graph, O of N square. Now we are bringing it down to V log V or N log N, right? So questions around that we could ask, but beyond that, we don't really test you on this part. Okay. Yes, so that is all I had to share with respect to randomized SVD and spectral clustering. So final suggestion, right, for the exam, I would say attempt spectral clustering questions, JLMA questions first, and then go on to LSH and what is the other one? Randomized SVD, right? Or randomized SVD and LSH. So from my understanding, spectral clustering and JLMA might and probability basics, right? So those parts might be easier for you to solve. The others could be quite hard. So yeah, so that is all I had. Anything else that you want to discuss?
About the choice of PUV, so you mentioned the effective resistance of this base methods and pseudo-inverse based methods. Is there any other method to do this PUV, like random some matrix of initialization? Because anyway, this PU, the matrix of probabilities will match with that of the initial uh, matrix that we start with, the dimensions, I mean. So is there something like a Gaussian initialization or something which might help, or it has to be something like this?
You mean instead of using this pseudo inverse, is there some other matrix that could help? Is that what you're asking?
So for initializing probabilities, basically PUV is for each edge in the graph. So
Right,
which means we need probabilities for every edge. Which
right.
means basically we need a matrix of same size as of the initial matrix A or whatever we begin with.
Right. Yeah.
So some Gaussian initialization or some there are other random initializations we use in deep learning also, right? So anything like that is there, or it's only this?
I'm sorry, Ganesh. I'm actually not very sure about that. So you'll have to ask the prof. That part I'm
Okay,
also not sure. Yeah. You have to plead ignorance there. So this
and
itself,
here
right?
it's
Yeah, go on. Please go.
Here it says it's proportional to this matrix. Like, what does proportional mean here? Is there any constant going to come in, or again, is there anything else, some more random process on top of this?
So what I understood, I'll tell you. So this is not necessarily between 0 and 1, right? So you all that you can say is this is some quantity. So you have PUV proportional to this for all UV pairs in all n choose 2 pairs, right? So I am guessing what you could do is compute those n choose 2 values. Okay, so you'll have and then divide by
I
their
think
sum.
I think what the professor had said in the lecture is that depending on how many edges are going out from each of the nodes or points, this the value or the weights start varying, so that you get more weightage or less weightage depending on how important the edge is, the effective resistance. So he was saying that this implies that effective resistance is just like calculating distance, and that's how he introduced J lemma. So the other thing he had said is that basically that means that if your edge is very important, it becomes the distance or the value becomes higher, and if the edge is not so important because there are many paths between the vertices of the two edges, the the value goes down and thus the probability goes down. And then basically this output is are numbers which you then normalize to get the probability spread. And he said these distances are approximately can also be approximated using JL lemma for the same reason, that JL lemma also will give you monotonically increasing or decreasing uh, value. I would not say monotonically, within plus minus this epsilon.
Right, right. Yeah. So yeah, regarding the actual normalization, right? I'm not very sure. So how do you so you have some values that so assuming that you can actually compute LG pseudo inverse, right? Exactly. You can actually compute EU minus EV transpose LG pseudo. This quantity can be computed exactly, right? So you'll have n choose two such values, but then they are not really probabilities, right? So how do you turn them into probabilities? You have to normalize, but then
A min-max would definitely turn them to 0 to 1, right?
right, yeah, but then what I'm not sure is these are probabilities, right? So strictly speaking, the distribution, so they should, what should sum to 1? Something should sum to 1, right? So I don't know what that, or what you should actually compute the sum.
What he had said is you take 1 and divide by the sum of all, and that way it will normalize to 1.
You mean one, all the
That
outgoing?
means you take, let's say, P11 divided by all the summations of all the P's, and then you do that for all of them, they will all add up to 1 eventually.
Correct. Yeah. The question is that the valid? Is that valid to? Is that the right thing to do? I'm not sure.
I don't know if you can call it probability, but that's how he had explained it.
Right. Right.
My understanding is that this entire probability matrix need not sum up to 1. Like if we need to do that again, the standard way to do that is softmax. But then to do softmax on n square size matrix is huge
Hmm.
computationally. So probably I don't think that is what we are doing. Might be something like a min-max normalization or something. But like you said, it won't add to probability equal to 1 for the entire matrix. But it need not, right? Because for each edge, they are calculating a probability of retaining that edge, and that's it. So the probability that needs to add up to 1 is retaining or not retaining. So
Right.
P
Right.
plus
Yeah.
1 minus P, that's it.
Right. Right. Yeah. That makes sense. Yeah. See, there are things like this which are kind of for which I also don't know the answer. So in one of the earlier sessions, I had shared a doc with some of them, right? And I had asked them to fill their questions there, which you might want to ask the prof, right? And if there are more such questions, so this is one, and say something in the power iteration part, I would like to ask the prof, right? So if there are questions like this, you can please make a note, and we can even request the prof to come and do a live session before the end term, provided like all of you will show up to that live session. It might be better to.
Definitely, yeah. We can definitely have one. It will be fine.
Sure, yeah, we'll try to do that. Yeah, anything else? Yeah.
Sir,
In
in
the
the
power
power
iteration,
iteration,
Yeah, you go on.
same question, I think. Basically, in power iteration part, when you showed that for loop,
Yeah.
do we have the time complexity calculation for the entire thing?
So according to the lectures, it's what MNLQ, right? Or MDL and Q. So this is okay. I haven't added it here. So this is ML square again. So this is the main part, right? So we are doing this Q times. So this is N cross M and N cross K, right? So M and K, this would be what I'll have to write it down. Uh,
I
yeah,
think it was MNLQ, something like that. Yeah,
There's a product of those four quantities.
yeah, yeah. In the lecture, it is given as MDLQ. Here, D is replaced by N.
Yeah, MNLQ. Yeah, that would be the complexity. So there's a trade-off between how many times you can iterate, and so the more you do, the better will be the gap between the eigen values or singular values. But then you have the time complexity will also blow up. Is that the question? Was that the only question here?
No. Yeah, my question was this ortho normalization that we are doing in the loop. Is it meant to prevent, this overflow or underflow of the calculations in a, iterative methods? Because we are repeatedly multiplying the matrices, so there may be a risk of overflow or underflow happening. So is that the reason we are doing this ortho normalization in every iteration?
Yeah, perhaps. So see, that's what they, in some of the resources that I looked up, it was mentioned as numerical stability, numerical efficiency. Perhaps that's what they're referring to. So let me once again, let me try to pull up exact resource. So if this was
Yeah, because that is the key challenge in all these iterative methods, how to prevent those overflows and underflows.
Right. Yeah, that is similar to that is what they had mentioned. Okay. So, yeah. Yeah, so this is the paper that I referred to. So what they are claiming here is, I think, similar to what you said. So this is basic subspace iteration. So this is A transpose Q, and then so the same notation in fact is being used, right? So you compute the first, you have the sketch A omega A transpose for Q, compute an orthonormal basis Q for Y. So that would be ortho of Y. This is where subspace iteration actually comes in. Now, what they are saying here, these are the lines. So for better, so we have presented algorithm 2.1 in an oversimplified way. So this is not exactly how they do it. So in practice, the computation of Y would be prone to round off errors, whatever you mentioned, right? So for better numerical accuracy, algorithm A.1 in the appendix should be used. So what they do is, after every few iterations of the inner loop, they balance it by doing a QR. So that's what appendix A.1 is. In fact, they do it after multiplying by A transpose and then after A also. So that's what they do here. So if you notice, they start with A omega, they first orthonormalize it to get Q, and then they multiply by A transpose, immediately orthonormalize with Q, and then they multiply by A orthonormalize to get Q. So they do it twice, in fact. So in the slides, we are only doing it once in the course slides, but apparently you can even do it twice. Yeah, for numerical stability is what they also claim. Okay, but exactly how this works, I'm not sure. So this is all I also could gather.
Okay.
Okay, but yeah, what you said seems to be correct. It's for some kind of numerical stability that they do this part, right? So they in fact do one more step Q here, but we are not doing that Q extra step there.
So in this slide, shouldn't it be Q is equal to QR of Z?
QR of, okay, yeah, that's correct. Good point. Yeah, so this should be QR of Z. Yeah. Second, let me change it.
And since it's Z directly, can't we just write, can't we just make Y is equal to AA transpose of Q and just do it for Y?
So
why are we splitting it into two steps?
So that is because of the size of AA transpose, right? So AA transpose is M cross M. So to compute AA transpose would be huge, right? So M cross N cross M. So M square N, right? So in fact, Prof writes it as MD square in the lecture's notes. It's actually M square B. So A is M cross N, right? If you want to compute AA transpose in one go, you would have to spend O of M square N time, and that is too much, right? M is bigger here. That's why we split the A transpose part into two steps.
Understood.
Okay, yeah, thanks for pointing this out. This actually has to be QR of Z. Yeah, anything else that we have to discuss?
Can you just show that slide on PUV proportionality?
Which one?
The last slide on spectral cluster.
Yeah. So this one I have changed to Z. So where is the PUV?
Okay. So although we are retaining nodes, it is probability P, but the P itself is retaining some edges more than the other.
Yeah, some edges are going to be more favored than the others. And
Yeah, right.
right. That depends on think that's where the Laplacian's pseudo inverse comes in. So that will kind of tell us properties of the Laplacian will point us to those edges which are prominent and which have to be given a greater weightage. Okay. Anything else that you would like to discuss? If not, we can.
Sir, for the future generations, why don't you do 2 quizzes instead of 1 quiz? Because this 6 weeks content is too much and it's complex also.
Yeah. So actually, the idea was Prof wanted it to be a midterm end term kind of format. So 1.5. It would have been ideal for a 1.5 hour paper and then end term paper. Yeah, we can. We'll also think about it. Yeah, we'll ask him once and see what he has to say. Yeah, we'll take that forward. Yeah.
I also have another suggestion. It's a serious one, but still. Can we please consider another programming assignment?
Another one, the question is what we will ask is quite unclear now. So see, the rest of the weeks are going to be not about algorithms. So they are all going to be about analysis of, probabilistic analysis of classification methods, right? So in general, so there is no scope of any programming assignment in the last 6 weeks, unfortunately.
I meant some other means of catching up in the curve, given the let's say the exam is tough, so we need some means of catching up. I mean, useful means of catching up.
Right. Yeah. We'll think about it. I don't know what can be done right now. Programming assignment, maybe we can think of.
Not programming, it could be something else, but please do consider it. Of course, I mean, it has to be something that contributes to the overall course as well. So
Yeah. So we'll think about it. Yeah.
So you
all
can
right.
ask us
Thank you.
to draw all those plots for FPR and TPR. How do they vary with K and L?
Yeah.
Something along those lines.
Right. Yeah. We'll think about it. Yeah.
I think Anupam is asking for another 5 marks bonus assignment so that
Yes,
we can
yes.
make up.
Yeah, no mystery about that.
Yeah. So I understand. So yeah. Yeah.
I mean, yeah, I would not call it bonus. I would rather spend effort and earn it. I mean, from that perspective, yes. So just like the programming assignments are quite interesting. I've only done half of them so far, but they're good hands-on. I mean, exercises, right? So if there's something else which can work both ways for the students as well as our knowledge and contribute to the course as well, so maybe we can consider that. That's what
Sir,
I
on a
meant.
serious note,
Yeah.
in the mathematical foundation of JNI, as well as in this course also, I felt that these programming assignments also help us in enhancing our understanding of the mathematical equations and all that process. Because it's just looking at the mathematics was giving us partial knowledge, but when we looked at those coding things, there was definitely an enhancement of in our knowledge. So that's a good concept.
Right. Agreed. So the question is how are we going to do that in the last 6 weeks, right? So last 6 weeks are. If we have to do it, we'll have to once again revisit the first 6 weeks and see if we can add a few more questions there. Yeah, we'll think about it, right? So I can also check with the prof what we can ask. So he might have some better ideas. Okay, yeah, we'll do that. We'll think about that.
Or just make the
Thank you.
first assignment to 10 bonus marks instead of 5.
That is also possible. So that's also not ruled out. If the quiz 1 proves to be incredibly hard, then yes, that is very much on the cards. But yeah, we'll check with the prof. Okay, I can't. Maybe he'll have some other better suggestions to offer. So I'll get back to you once.
Okay.
About the choice of K in randomized SVD, we discussed the relationship between K and L. So that L is just marginally larger than K. But then choice of K itself, how do we choose?
So yeah, P, right? So P, from what I read, it seems that a value of 5 or 10. So this is again a very good review paper on this. They mentioned that P equal to 5 or P equal to 10 seems to be more than enough for applications.
I'm asking about the K.
K, you mean?
So-
Oh, okay. K, right. So K can be tricky because we don't know what K has to be, right? Depending on what.
Yeah, something on the lines of elbow was mentioned,
Right,
right?
right.
But then to do elbow, you'll have to run
Get the
for
singular
various
value.
values of K.
Right. So you need to have the values, singular values, in the first place to
Yeah,
get hold of the K.
to directly know K, or you will have to run multiple iterations for a reasonable range of K, and then pick out a K near an elbow, something like that, where it would give a reasonable. Because we will have the SVDs of the smaller
Right,
matrix
right.
that we generated.
Yeah. So
But
this
then that
also.
again will increase our complexities to MDLQ and again some values of K also.
Right, right. Yeah. So what I would request you to do is, these are things which are beyond me also. So there is no way I can be of help here. So this is a form that I had shared, not a form, a doc that I had shared with all students. One of the sessions. So I'll share it with you here. Okay. We have already added some couple of questions. So
Can you put this on the space?
yeah, I'll do that.
Yeah.
So this is, you can also mention this bonus or extra activity, that also can be mentioned. So I'll give sharing permissions to everyone. Can you edit, by the way? No, right? Most of you can't edit. Anyone in the group can edit. So, okay. So this is spectral clustering, randomized SVD. We had some questions in spectral clustering. So randomized SVD, you can ask, how do we. So, okay, I'm not sharing the screen, right? So, one second. So, maybe we can add it now itself so that we don't. How do we choose K, right? How do we choose K? You can add other questions. So, there are some general questions you might want to ask, right? So, one is, are there other. Quiz 1. This is for any future terms, but can we add a quiz 1 for future terms? Okay. And can we have one more programming assignment or some other activity, right? Extra activity. So this I'll ask the prof. This one I can ask the prof. And so others, you please note it down, whatever questions you have, and I can share this with him, and he can then get back. Okay, yeah, what happens to the points between? Yeah, that no one knows.
It's 9 o'clock.
Unfortunately, hope he knows that part, so we'll have to ask him. Anything else? If not, you can maybe continue editing this, maybe through next week, and then we can take it to him.
No, nothing else.
Okay, right. So I'm stopping the recording now.